So I don't have any slides prepared, unfortunately, but what I'll do instead, I think. So I want to talk about the process of implementing a Stark prover, which is something that I've been doing over the past couple of months. And obviously, the purpose is not so much to explain Starks, because we're talking about Groth16 specifically. But the reason I think it's still very interesting is because I spent a lot of time implementing a very efficient prime field library. And I want to talk about some of the complications and challenges that you have in implementing such libraries. This is pretty low-level stuff, and in the case of Groth16, there's an excellent library out there already called Bellman that has pretty good performance. Despite that, as you will see, I still managed to beat Bellman on essentially any operation. Not by much though, except when it comes to field inversions. But the reason it is the primary reason it's interesting to revisit how to implement something as low level and mundane as a prime field is because the expectation is that most of the opportunities to scale Groth16 are going to be from moving it to GPUs. And once you're on a GPU platform, you need to re-implement everything from scratch. And one of the things you'll have to implement first is actually the thing you need to implement first before you can do anything else is a prime field. And in fact, once you've implemented prime fields, the rest is more or less straightforward. Because then you'll, once you have a prime field, everything else is just operations over this prime field. Like once you have addition, multiplication, inversion, etc., modulo some large prime, anything else can just be expressed as those field operations. And the rest of the implementation of Groth16, I expect, will more or less follow what has been done in the CPU implementation, with the exception of some more opportunities to exploit parallelization. But none of that has any value unless you manage to get field operations faster than they can run natively on a CPU. Let's see. Now, I've been looking into GPU implementations of prime fields, and it's a pretty hard problem. Fundamentally, in prime fields, you have at least 256 bits that you want to use for cryptographic applications, and these interact heavily. If you look at prime field multiplication, in fact, I can show you how these are implemented. Where is my feed? So if we look at a full multiplication, can everyone see my code? Is it readable? I can try and make it a little bit larger. I'm not getting any feedback.
Yeah, I can see.
Okay, good. Thanks. So this is how you would implement a field element, a 256-bit field element. Basically, you start with a primitive, which is just a 256-bit number. And since CPUs don't have a native 256-bit integer type, you need to somehow construct this out of smaller integer types. So in this case, it's being constructed out of 4 64-bit integer types. Together, that gives you 256 bits, which is sufficient to store every field element in. 64 bits is sort of optimal for modern CPUs because this is the largest integer size that fits in a register and that has native operations. A lot of languages nowadays also give you a 128-bit type. I would recommend you avoid this one because it's more or less emulated. There are some instructions on a modern processor that have something to do with native 128-bit types, but most things like add with carry don't really exist, and the compiler ends up generating code that emulates it, and you want to avoid that. You want to have good control over the low-level implementation of your prime field. So that's why you pick the integer type that's most native to your system. There are other ways of doing this, especially if you look at earlier libraries before integers were 64-bit. Honestly, that is a big deal. Like 32 bits is of older processors is significantly less to work with. Some mobile embedded systems are still stuck in things less than 64 bits. It basically, the number of operations is 4 times more once you go from 64 to 32 bits, because you end up, instead of having 4 numbers, they're called limbs, by the way, in the GMP parlance. GNU multi-precision is the state-of-art library. So yeah, whenever you want to know how to best implement something, just take their notes. It's awesome. They spend a lot of time in this. So yeah, one of the early decisions you need to make when implementing any kind of number theoretic library is how are you going to represent the large numbers. And in modern CPUs, 4U64s is a good one for 256 bits. This is also what Bellman does. If you look at libsecp 256K1, the C version, which is probably the most optimized piece of cryptography out there, like by any stretch, you'll see that they actually use a slightly different implementation where they use 5 words of 64 bits, even though they only need 4 technically. GMP also does a similar trick where it actually uses more limbs than necessary. And what you then do is you have these 64-bit limbs, but you only use something like the lowest 52 bits out of them, which means that you have some extra headroom in the limbs themselves. And this gives you an advantage in, for example, addition. Because if you add 2 numbers, you start by adding the lowest 2 limbs together, just like you would do on pen and paper, right? You would write the numbers down left to right and then start from right to left, adding them up, taking the carries everywhere. If you have extra space in the limbs, you don't have to propagate the carries immediately. Like you can add the rightmost digits, and since they're always only 52 bits, the result is going to be at most 53 bits, and this still comfortably fits within a 64-bit number. So you can delay propagating these carries because you can still successfully represent the numbers. They will not any longer be unique representations. Plus, eventually you will need to propagate the carries. So you need to take that into account, and it makes your library substantially more complex. Which is why I haven't implemented this yet, and which is why Bellman doesn't implement this particular trick, but GMP uses it. So there must be something to it. And libsec P256K1 also uses it. So yeah, worth looking into then. Now, why would they use this trick? The reason you want to do this is, again, because you're avoiding carries, you have no longer any data dependencies between the limbs. So if you're guaranteed that you don't need to propagate carries, which for a lot of algorithms you can prove, at least for addition and subtraction, you can process the limbs in parallel. Which like you don't need to compute the first limb in order to compute the second one, because you don't have to add the carry. This gives a huge speed boost on modern CPUs because they have complicated instruction schedulers and register assignments and everything. And basically the CPU, by looking at your code, can figure out that it can execute these two instructions in parallel, and it will actually do so. Let's go on another random side street. So how modern CPUs work. Basically, a modern x86 64 processor is actually a virtual machine that pretends to be an x86 64 processor. And one of the first steps it does when it loads instructions from memory is decode the instructions. And then they get converted into something called microcode, which are more like long instructions that say something like, hey, load this register into the accumulator, tell the accumulator to do an add, pull it to this register, and so on. Like it transforms your code into something completely different. And one of the things to know is that even though the instruction set only gives you something like 16 registers, 16 64 registers, the actual CPU has many more registers, something like in the order of 200. And during the x86 code analysis phase, it will just relabel registers. And the CPU will recognize when operations can happen in parallel. Like a single thread actually has access to, I think in modern Intel processors, it's something like 4 simple ALUs that can do binary operations, OR, AND, XOR, etc., and addition, subtraction, and 2 multiplication units, multiplication/division units that can do like 64 multiplication or 64 by 64 division and so on. They can actually do one more trick that we'll get into later, which is a 64 by 64 to 128-bit multiplication. Anyway, so you have this processor that sees a stream of x86 instructions. It has a bunch of registers available. It has 2 BV algebra units. You can do multiplication and division. And it has 4 simple units. And basically, your processor runs complicated firmware called microcode that tries to use these things optimally. And it will run a decent amount of instructions in parallel if you design your algorithms to do this. And in prime field implementations, this is really hard to achieve, this sort of parallelism, mostly because of the carry propagation. This is, by the way, why binary fields are so interesting, because this is pretty much the same thing as a prime field, except they don't have carries anywhere. Hence, they are efficient. But their multiplication is different and less supported. Let's not dwell into that too much. The reason I'm spending so much time on explaining why you want to look into over allocating your limb size, having some spare bits in there, is because once you move to GPUs, this is going to become really important, because the overhead of interacting between parallel variables is much higher on a GPU versus a CPU. So yeah, you definitely want to look into this as a technique for implementing it. Another thing is that I think GPUs only recently started to get 64-bit support. Most of them are still stuck in 32-bit. So I'm not sure how useful it's going to be to use a 64-bit representation. There is another alternative representation that is worth dwelling on a little bit, especially for GPU applications, but surprisingly also for WebAssembly. So we've stuck with integers so far, but you can actually do prime field math using floating point types. Especially like a floating point double gives you, it's essentially a 52-bit unsigned integer, a 1-bit sign bit, and I think an 11-bit exponent, with the exponent itself also having a sign bit. Is that right? I think I got the numbers off slightly. Anyway, it's something like that. The important bit is that any double size floating point number still contains 52 bits of essentially unsigned integer that you can use if you're clever about it. Like if you stick within the 52 bits, then addition, subtraction kind of work as expected. There is some caveat having to do with how it adjusts the exponent. Multiplication is different though. If you do regular U64 multiplication, you'll end up getting the result modulo 2 to the power 64. Meaning that if I multiply two large numbers and it would overflow, I only get the lowest bits of the results. The highest bits are hidden from me. If you do floating point multiplication and you multiply two large numbers that would overflow, instead of getting the 52 lowest bits, you actually get the 52 highest bits, which changes the way you would implement your fundamental algorithms, but it's doable. You can actually use this and get a high performance prime field library. And back before 64-bit processors were a thing, one of the fastest elliptic curve libraries out there was one done by Daniel Bernstein. If you haven't come across his name, look him up, because the guy is a god when it comes to implementing crypto libraries. And he has invented pretty much anything out there, like at least made the best implementation of it at some point in his life. So he also made one of the best implementations of a floating point based prime field library. This has an advantage back in the days of 32-bit processors, because they already had 52-bit floating points, like double floats back then, which meant that you could work with 52-bit integers instead of 32-bit integers. And this gives you like, what is it, a 1.7 multiplier in the amount you can compute at one go, which actually ends up giving you a like quadratic boost once you get to multiplication, which is usually your bottleneck. So this is a decent optimization to make. This is historical, but I think it's worth revisiting, again, because of the GPUs. Modern GPUs are, like a modern GPU is essentially just 1,000 Pentium 1 processors next to each other. So you have access to 32-bit registers, almost no internal parallelism going on, but you also have access to floating points. So if you find yourself with a GPU that doesn't give you 64 bits, but it does give you double-sized floats, then you can look into this old trick to use that to get 52-bit math and implement your library around that. But like I said, fair warning, multiplication will be very complicated because you're not working modular, but you're working with the high bits instead. Another area where I can see opportunities for this little trick is actually in WebAssembly. let's see. Before I go into that, I need to explain one thing. So like I said, standard x86 multiplication, if you multiply two 64-bit numbers, you get the lowest 64 bits of the output, but there is actually a special instruction, which is hugely important for anyone doing number theory in big nums, that gives you the higher 64 bits as well. So there is one instruction that does a 64-bit by 64-bit multiplication and gives you access to the full 128-bit output. This is the molq instruction, and this is an instruction you pretty much only see in cryptocode, and inside cryptocode it's probably where most of the time is spent. So that has been like hugely important. ARM in like, I think since about a year and a half or 2 years or so, also has this instruction, or at least something similar to it. Like there are two multiply instructions. One gives you the lower bit, one gives you the higher bit. So you can do the same thing. So basically your code will be portable between x86 and ARM if you use this large multiply. In fact, I have a utility function called mac here. You'll find identical functions, even identically named, in many number field libraries. Bellman has an instruction just like this. In fact, I think I copied it originally from Bellman's library. But basically, so this is Rust. So it's looking a little bit awkward because we need to do all this casting. All of this actually compiles down to pretty much one molq instruction, maybe with an addition in there. But we basically upcast all our, we want to compute A plus B times C plus carry. You can show that this expression will never overflow as long as these numbers are 64 bits. Like the result will always fit within 128 bits, which is not obvious because we're adding two numbers to it. So yeah, what we do, we just cast everything to the like fake compiler 128-bit type. We do the expression and then we cast it back to 64-bit types and we bit shift to get the higher bits out. All of this you're seeing here is completely fake because it doesn't end up actually doing anything in the resulting machine code. And Rust passes it along to LLVM. LLVM is super fancy and recognizes what is going on here. And it recognizes that we're just trying to do a 64/64 to 128-bit multiplication. And it just replaces this with a single molq instruction. So that's what's going on there. Now, this instruction doesn't exist in WebAssembly. And there is a proposal in progress that I'm sort of half involved with to add this instruction, since it is like supported on their two main architectures that they want to support, being ARM and x86-64. So what do you do if you're lacking this instruction? And on a GPU, you will be lacking this instruction. Basically, without this instruction, performance, you need to manually implement this multiplication. And the way to do it is by just converting your 64-bit numbers to 32-bit, and then using a 32 by 32 to 64-bit multiply, which is just a regular 64-bit multiply that is available. But this means that every like molq instruction would get replaced by 4 regular multiplication instructions. So you and there's a bunch of bit shifts and data reorganization going on. So this is like a substantial performance killer if you need to go this route. In WebAssembly though, we have, I mean, for the rest there are, the registers are 64-bit, so addition and everything can happen in 64-bit. We also have access to doubles. So one funny trick that I wanted to implement, but I haven't gotten around to do it yet, which could be like a fun little project, is if you use this expanded limp process where you only use 52 bits of the limp, and you remember that, so now we can do a multiply, and we will get the lowest 52-bit of the result, right? Because we can do a regular 64-bit multiply with them, and then we'll get the lowest 64 bits of the result, which also happen to contain the lowest 52 bits of the result. Then we can also do a double floating point multiplication, which will actually give us the highest 52 bits of the result, which means that we now have the total 104 bits of the result, which means that we can, with 2 instructions instead of 4, do a 52-bit multiply on an architecture that doesn't support this natively. I suspect that this trick might not actually be super useful on real architectures such as x86 or GPUs, because usually moving data between floating point registers and integer registers is a fairly costly operation. It's not optimized much, basically because it's not used much. But depending on how your WebAssembly virtual machine is implemented, the instruction loading overhead might be higher than whatever is necessary to do the internal moving of data. So on WebAssembly, it might actually be a performance boost to do things this way. And maybe on GPUs it might too. I don't know. It depends on how they're implemented. Could be worth testing. Anyway, that was a lot about this 5 lines of code here, but this is where all of your main decisions are made. By the time you have this thing, pretty much the rest is all of your basic operations are defined right there. So once you've settled on how you want to represent your numbers, addition is straightforward. Let's see if I can find my little add routine. Bit shifts. There we go. Add. Yeah, it's straightforward. You have 2 numbers. You take their lowest bits. So the left one, coefficient 0 is the lowest bit, the lowest limb. You add them together, you get a carry. Then for the next 2, C1 and C1, plus the carry from the previous one, and so on. And you just progress upwards through the thing, propagating carries, computing the new result. That's it. Subtraction is similar, but instead of carries, you have borrows, and you just borrow from the next limb and so on. So that's straightforward. Mind you, we're still just working in 256 bits. We're not working modulo 2 to the power 256. We're not working in our prime field yet. Before you can get to the prime field, you need to have integers that can represent elements of the prime field. So we're just implementing that at this point. Let's see, the other interesting routine, and probably the most interesting routine in your entire code, is going to be multiplication. In this case, this is a full multiplication, so it takes 2 256-bit numbers, and it results in the highest 256 of the result and the lowest 256-bit of the results. And the amount of instructions here, you can see all these max. These are like the 128-bit result multiplications I was talking about. And as you can see, there is 16 of them. And this reflects the fact that we have 4 limbs. So your multiplication routine grows quadratically in the number of limbs that you have. So if you go to larger numbers, you are forced to have more limbs, and your performance will suffer quickly. Until some point, there are actually more efficient algorithms like Tomb-3 that grow better than quadratic. Problem with these methods is that they don't really result in practical performance gains unless you hit 1,000-bit numbers, which in the sort of zero knowledge stuff that we're doing, we won't find. So yeah, multiplication grows correctly in the number of limbs. This also means that if you go to GPUs and you're forced to use 32-bit limbs, then your performance drops by 4 right there, because now you need to use double the number of limbs. And GPUs need to like offset this this by being 4 times more performant, which is tricky. Let's see how that pans out. Again, this is just basically schoolbook multiplication. So you take like the lowest limb of the first number, multiply it by all the limbs of the last number, and this gives you a like temporary result of 5 digits. And there's always like the carry. And the next one, you start with the second limb and everything gets shifted by 1 limb and so on. And in the end, you'll end up with a 8-limb result that you can store in 2 of your U256. If you're squaring a number, if you're multiplying by itself, you'll find that some of the limb multiplications you're doing are redundant. So you can replace them with, for example, with shifts and adds and things, which simplifies it. Let's not go into division and inversion for now. No, actually we need to, because you need it for the modular operation. So these, so addition, subtraction, multiplication are the simple stuff. However, we are talking about a field which also has inversion, and inversion is where things get interesting, and the number theoretic libraries, you separate the boys from the men here. So there's a simple thing you can do, which is use Fermat's little theorem and just multiply a number by itself a whole bunch. No, that's for prime fields. Hold on, let me not mix that up. Actually, there is a similar trick that allows you to do inversion in U256 using Hensel lifting lemma. It's a trick that allows you to do really fast inversions modulo 2 to the power of 256 using just a couple of multiplications. It's basically doing Newton-Raphson iteration on the inversion function. Newton-Raphson you might know from numerical analysis to like find roots and polynomials over the real numbers. Funny thing is, it also works in modular numbers, when you have a result, and there it works in sort of a p-adic way, which means that if you know the result accurate in like the last 4 bits, you can expand it to 8 bits and to 16 bits and so on. So like if you want to do inversion mod 2 to the power 256, you can just start with, like this happens to be a good seed value, 3 times the lower 64 bits of your number XOR 2. This is your inversion modulo 2 to the power 4. Then we do 2 minus like the lowest 64 bits of our number times the intermediate results we have. This is just like standard 64-bit math. Now we have the result accurate up to 8 bits, 16 bits, 32 bits, 64 bits, and so on. Now we need to shift to 128-bit math. We get it accurate to 128-bit. And now we need to do 1 time the same operation in 256 bits. And we have our final result. And the observation here is that it's like you can do inversions mod 2 to the power 256 with basically one multiplication and a couple of like just 64 bits operations, which really doesn't amount to much. So that's a really cheap operation if you implement it cleverly. All right, but this doesn't really have applications when you're implementing elliptic curve, because you need to use prime fields. So we need to invert modulo some number that is less than 2 to the power 256. Kind of the standard simple way to do this is using the binary extended GCD algorithm. You can find this in the Handbook of Applied Cryptography. This is a book that is freely available online, and it's really freaking awesome, and definitely look into it. And basically it computes the GCD, the extended GCD. So the extended GCD gives you a bunch of numbers such that, let's say we want to do the extended GCD of numbers x and y. That will give you numbers a, such that a times x plus b times y equals so yeah, it results in a GCD. So that you get two numbers such that a times x plus b times y equals the greatest common divisor of those two numbers. And the way we use this for inversion is that, let's say we have our number n and we have our modulus. Since the modulus is prime and larger than n, the GCD will always be 1, and we will end up with a set of numbers such that a times n plus b times modulus is 1. If we take this expression and do it modulo the modulus, we get a number that is a times n plus, okay, so this is b times modulus. So modulo the modulus, this is just 0 equals 1 modulus. And what you see here is that now we have a number such that when we multiply it by n, it results in 1, meaning that a equals 1 over n modulus. So this is how you use GCDs to invert numbers. It's the fastest way to do it, but you'll find that in many libraries they actually use Fermat's little theorem. Which goes like this: any number n to the power of the modulus minus 1 equals 1, or equivalently, like to the power of the modulus equals n, or if we do modulus minus 2, we get n minus 1, i.e. the inverse. So what you'll see happening and when you implement something you don't care too much about inversion is that you just use your multiplication using square and multiply to just exponentiate something to the modulus minus 2. It's valid. It has one advantage, which is why it's actually used a lot in elliptic curve libraries. It is predictable. Like, this method, when you implement it, is always the same sequence of multiply operations, which means that it runs in constant time. So it will not be susceptible to side channel attacks and things. This is why you see it a lot in elliptic curve libraries, because they need to be protected against this. But this is a compromise, because this method is actually substantially slower than the GCD based one. But as you can see here, this GCD is like full of while loops and ifs and branches, which means that the path and all these branches depend on the input values. So like the path your code is taking depends on the input values, and like cache misses, energy consumption, you name it, everything is going to leak your private keys if you're trying to invert your private key using this method. For zero knowledge proving stuff, even though in theory we should worry about side channel attacks, we really don't. We cannot, because we cannot afford the performance drag. Like we just prefer to physically protect our servers from side channel attacks. Or another way to look at it is that there is so much data going on that it would be very hard to like distinguish signal from noise in all of the operations that are happening. But that's kind of a heuristic argument that's probably not going to be true forever. Anyway, you want to use GCD based methods here. That's the point. So GCD based methods have two versions. There's binary GCD and there is the Euclidean GCD. If you're just doing a naive implementation, binary GCD is going to be fastest because it ends up just doing a bunch of bit shifts and additions and subtractions with some conditions in there. Whereas if you use Euclidean GCD, you need to compute the remainder. Compute the remainder at every iteration, the quotient and the remainder. And this is an awkward operation. Like we haven't gone into how you do division and remainder in U256, but I can just show you the code and it'll give you an idea of the complexities involved. Of like it's a separate file just to do divisions. This one implements algorithm D from Knut's The Art of Computer Programming, volume, I think it's 2, semi-numerical algorithms. Definitely get a copy of that one too, whenever you're working on this stuff. Knut's books are the Bible in this field. He was personally responsible for finding some of the fastest methods out there. I think when it comes to GCD, he was pretty much involved in fleshing out the best algorithms. And for small values, like the ones we're working with, these methods are still the best ones out there, and they're used in GMP, for example. So you definitely want to look into them. They're not easy though. This particular one is notoriously hard to implement. So most number theoretic libraries, especially the ones in crypto, they just skip it altogether because like the idea is you want to avoid divisions anyway. So they end up not optimizing them at all. If you don't optimize it, there is something called Egyptian division, where you basically do like standard schoolbook division in binary. So you look at the binary expression from left to right. If there is a 1 there, you take your divisor, you shift it until the first one aligns, and then you subtract it. And you keep doing this until you have your division result. Anyway, so that's why binary GCD is like easiest to get going. It ends up though that in the end, the Euclidean GCD is actually faster if you implement all the little optimization tricks. And I have an implementation of that here. At least I thought I did. Where do I have it? Hold on, maybe this. Maybe on an old branch. There we go. Lemur's GCD algorithm. So this is the state-of-art way to do GCD computations in like large numbers, and by extension, it is also the fastest way to invert sorry, to invert numbers modulo a large prime. Let's see, how are we on time? Oh, okay. I haven't even gotten to the prime field implementation yet, and we're almost out of time. Yeah, I'm not going to go through this method. It is really large and more complicated even than the division one, but it is exceptionally fast. Let's see if I can just pull up the performance numbers. No, not in a compiling state, unfortunately. So yeah, this is the method that GMP uses, but GMP uses it for arbitrary length, and we have an advantage here that we know upfront that we have exactly 4 limbs, so we can optimize for that. We can inline a lot more stuff. We can unroll a lot more stuff. So this implementation actually ends up being twice as fast as GMP's. And compared to Bellman's inversion routine, which I think just uses Fermat's little theorem, we're looking at like a 10x, 50x improvement. It's like 1 or 2 orders of magnitude faster, which is a really interesting result, because like traditionally the assumption is that inversion is going to be so slow that it is not worth bothering with in an elliptic curve library. But actually, if you use Lemur's GCD algorithm, you can get it decently performant. Like, it's only about 50 times slower than a multiplication. Which means that in some areas, it ends up being useful. So like, we won't be able to get here, but if you go to windowed non-adjacent form representation of elliptic curve multiplication and so on, and Jacobian versus affine form of points, if you convert from Jacobian form to affine form, you need to do a field inversion. And what I found is that given that the inversion is much faster now, I can batch invert my entire WNEF lookup table into affine form before I go into the WNEF routine, which means that instead of doing Jacobian additions, I now do Jacobian affine additions, which are a bit faster. So this leads to like a, 20-30% speed up. And it was enabled by just having this faster inversion. But yeah, that's like lecture 5 before we get into WNAF. Okay, so now we have our U256 implementation. You can start with like binary GCD to have a modular inversion in there. Then you get to the field element itself that you're implementing, which starts with having a modulus, which is specified as a constant of your U256 type. It's also common to store modulus -2 to do the Fermat's little theorem based inversions if you need it. And then basically you just implement it using the primitives you just created. Like addition, for example, let's see. You just add the field elements together, and if the result ends up being larger than the modulus, you select the modulus ones to normalize the result again. In this case, this is safe to do because my modulus has like a 0-bit in front. If your modulus is larger than 2 to the power 255, this will no longer work because addition can overflow your underlying integer type. So you need to take special precautions to check that. Multiplication, you can use the you can use the full multiplication you have in your U256 routine, and then implement 512-bit division to like reduce the result modulo your number. It's a bit of work to implement this. And like I said, division routines tend to be slow. So what you'll end up doing instead is use something called Montgomery Representation, which is a whole other area of trickery. Let's see, it's like 5 minutes left. So I won't be able to go through Montgomery Representation, but this is, what you basically do is you multiply, so where you have n modulo your prime p, you would instead compute a constant called r, which is 2 to the power 256 modulo your prime p. And instead of working with your numbers directly, you would work with n times r mod p. For addition, this doesn't like change anything because a plus b, like if I multiply both of them by r, it just moves out of there. And if we multiply two of these numbers, we'll end up with a result that is a times b times r squared. And this is the reason why we multiply, because there is actually a nice, cute little trick that computes like e times f divided by 2 to the power 256 mod p. And if we apply this trick on AR, BR, we actually end up with a result. So like we have this operation here that is somehow cheap. And if we apply that and we do like our funny operation here, then we'll end up with the product divided by R. So we get the product times R, which is actually in the form that we need for the, like in the Montgomery form already.
So hey Remco, yeah. Thank you so much for doing this. First off, I know we have like 5 minutes left. I just wanted to give you I would love it if you could tell everyone that's listening where they can find out more about you, about 0x, and about the work that you're doing.
Right. Yeah, sure. So I'm the scaling researcher at 0x. I research decentralized exchange scaling. During last year, I pretty much realized that zero knowledge is going to be the way to scale stuff, because a proof for a particular computation is significantly smaller than the computation itself. At DEF CON 4, I kind of pitched this idea to Starkware, and we started collaborating together on how to use their Starks for a decentralized exchange. This is now StarkDEX, and we have our demo live. We'll be open sourcing and releasing a whole bunch of this stuff. I mostly got into Starks because of the claimed performance by Starkware. In particular, the prover time, which is a main bottleneck when you use it for scaling, is actually really good for Starks. And we were sort of cocky in thinking that we could implement a Stark verifier in Ethereum, in the EVM, and have it within the block gas limit. That actually ended up working, to our surprise. So now Starks are a thing on Ethereum. They don't require any pre-compiled contracts. They can still be optimized a bit. Like the proofs are substantially larger than pairing-based cryptography ones. Anyway, so this is how I got into Starks and into implementing the mathematics behind it efficiently. That being said, I'm not like married to it by any means, so I'm also exploring other proof systems now that have their own set of trade-offs. And a lot of these optimizations and everything will just carry over. Like all of this code is fairly trivially reused to implement pairing-based cryptography systems. So this is why why 0x is so interested and eager in participating in the prover optimization challenge, because prover time is going to be the main bottleneck in any sort of scaling solution.
Amazing. Thank you so much, Remco. This was really awesome. And yeah, I hope you have a wonderful day.
Thank you. What are the next steps? What is the best way for people to, like if they want to contact me or anything? This library, unfortunately, is not open source yet, but I expect to do that really soon.
Yeah, I would just provide people with like ways to contact you on here, and then I'll be sure to include that in the description of the video for this.
Okay, sweet. I think best way would be either remco@0x.org or my Twitter handle.
Awesome. Thank you so much, Remco. I'll be sure to share this video once it's on YouTube. And yeah, thank you again so much.
All right. Thank you. Have a great day.
You too.